The next thing in our theoretical development is talking about maximal ideals, prime ideals, etc. But to give examples, at least some non-trivial examples, we need to know certain facts about polynomial rings. So I just want to review polynomial ring in one variable mostly, but a little bit about multivariable polynomials as well. And this is supposed to be a review material, so this will be very brief, just collecting some basic definitions and results, very little by the way of proofs and very little examples. I'm assuming that you're familiar with this material. So this is very much a review. And let R be a commutative ring. With one. I just don't want to think about when it doesn't have one. So a polynomial in one variable x with coefficients in R in x is an expression like this: a0 plus a1x plus a2x squared plus an x to the n, where the a1, a0, a1, etc. are in the ring R, and this x is thought of as a variable or an indeterminate. So a polynomial f of degree n in R with coefficients in R in R is an expression of the form f equal to this. Sometimes you say f of x, sometimes you just write f. If you want to think of it as a function, then you write f of x, where a0, a1, etc. are in R. And if I insist that the degree is n, then we should write a not equal to 0. And these guys are called the coefficients of f. This an is called the leading coefficient. Leading coefficient of f is the top coefficient, and degree of f is the highest power of x that appears. You can look up a formal definition, but we wouldn't bother. So two polynomials are equal if all the coefficients match. So sometimes it will also be convenient to write n equals 0 to infinity, where all aj are in R and only finitely many aj non-zero. That's what a general polynomial looks like. Yeah. And given two such things, and the advantage of writing it like this is that then you don't have to keep track of where it ends. After a while it ends, is what you're saying. And equal if aj equals bj for all j. And you add and multiply them in the usual manner. If you give me two such things, fx plus gx would be, if this is f and this is g, let's just write f and g, then f plus g is just an plus bn x to the n. So just add coefficients, that's simple enough. And when you multiply, that's a little more sophisticated. You go a0 b0 and then a0 b1 plus a1 b0 x plus a0 b2 plus a1 b1 plus a2 b0 x squared plus etc. So the general expression is ai bn minus I x to the n equals 0 to infinity, and here I goes from 0 to n. Yeah, that's how you add and multiply polynomials in the usual manner, and this forms a ring. It's called Rx. Rx is the set of all polynomials in one variable x with coefficients in R. And this is a commutative ring with 1. The 1 being the degree 0 polynomial, which goes like 1 plus, so 1 of Rx is the polynomial that goes like 1 plus 0 times x plus 0 times x squared plus da, da, da. Yeah, and this one is the 1 of R. And in this way, every ring element R, every element of R is naturally identified inside Rx. Identify. As degree 0 polynomials. And you can check the basic fact that if R is a domain, then when you multiply two polynomials, the degree adds up. That's sort of the key first thing that you have to prove. Let R be a domain. Everything sort of follows from this. And f g in Rx, then degree of f times g is degree of f plus degree of g. I guess to be exactly correct, I should say that these are non-zero. I don't know if I have defined the degree of the zero polynomial. If you want to make this true also for the zero polynomial, I guess you have to define the degree of the zero polynomial to be minus infinity. But so I should say non-zero polynomials. Then this is certainly true. And the reason is that when you multiply polynomials, the middle coefficients sort of get crazy, but the top coefficients just multiply out. So if you have a polynomial that starts with 3x to the 5 plus da da da, and another one that starts with 2x squared plus da da da, and these are lower degree terms, these are lower degree terms, when you multiply, you will get maybe lots of contributions to x squared, but you will get only one contribution to the 2x to the 7. That I'm sure of. It's coming from here and here, so it will be 6 times x to the 7. And since R is a domain, that says that when you take these leading coefficients, if they are non-zero, then when you multiply them, you still get something non-zero. And that's basically the proof of this. So that's why the degree adds up, because when you multiply, the top degree term of f and the top degree term of g are the only things that multiply out to give the top degree term of f times g. And a couple of immediate consequences of this I want to record. If R is a domain, then Rx is a domain, and C, the units of Rx are equal to the units of R. You see, R is being identified inside Rx. So of course if you take a unit in R, it's going to be a unit in Rx. But if you take some, so all I'm saying is that any unit of Rx, first of all, has to have degree 0. Because if it has degree strictly positive, whatever you multiply it with, it's still going to have positive degree by this thing. So you can never get a constant that way. So you cannot get 1 that way. Okay. So I guess next we have to talk about the evaluation at a point, but that will be the next video.